Tonight's presentation is titled Your Engine's Lifeblood. Our presenter is Mike Busch. Mike is president of Savvy Aviation Incorporated. He's an author for numerous aviation publications. Mike holds Certified Flight Instructor Certificate, A&P Mechanic Certificate with inspection authorization privileges, 2008's Aviation Maintenance Technician of the Year with FAA, and of course a member of EAA, and continuing in his weekly series of webinars. Mike, we're just so privileged to have you join us here at these weekly webinars, and so thankful to you for contributing to this community in the way you are. I'm going to turn control of the presentation over to you.
Well, thanks, Tim, and good evening, everybody. Tim, I don't know if you noticed, but while you were talking, I was watching the attendee count, and it crossed over 1,000 in the middle of your little dissertation there. So,
hoo, welcome everybody. That's awesome.
We didn't used to be able to do that. The new software, you could do that, so that's really cool. Very, very cool. Oh, and you mentioned Home Builders Week, and I'm actually going to be doing one of the webinars in Home Builders Week. I think I'm scheduled to do the very last one on Saturday, and it will be a webinar on engine break-in.
Very
which
cool.
Is probably something of interest to most home builders.
Absolutely.
Anyway, tonight's webinar is about engine oil, as you can probably tell from the slide. It's an interesting subject because the role of oil in our piston aircraft engines is pretty complicated because we rely on oil to do so many different things. Now, obviously, oil is there to lubricate moving parts, to reduce friction and wear, and we'll be talking about that. But lubrication is only one of 6 key functions that oil performs in our engines. And actually, in my opinion, it's probably not even one of the most important ones. And the reason I say that, obviously, it is very important to engines don't last very long running without any oil, and it is important to provide lubrication. But it's important to understand that the lubrication requirements of our piston aircraft engines, at least the direct drive ones that turn the propeller right off the crankshaft, and so they turn pretty slowly. Typically 2,700 RPM red lines. The lubrication requirements of these slow turning Lycomings and Continentals are very modest compared to what we're used to with automobile engines that turn much higher revs. And that's because lubrication demands tend to vary with the square of RPM. So a Subaru engine, which is the one I have pictured here, it's particularly high revving engines, got a 7,000 RPM red line. Its lubrication requirements are vastly more demanding than our 26 or 2,700 RPM aircraft engines. But we will talk a little bit about friction and wear and how oil plays a role there. And then we'll talk about some of the other things that we depend on oil to do. So the science of friction and wear is called tribology. Friction occurs because even the smoothest metal surfaces aren't really that smooth when you look at them very closely. What you're seeing here on the slide is a scanning electron microscope view of a polished metal surface. And you can see all of the little peaks and valleys that are on that surface. Now, those peaks and valleys are only microns in height. But that's what the surface of even a polished metal surface looks like. And the little peaks are known as asperities. And here's a closer look at that slide. But there's the surface of even the most polished metal surface is just full of these little asperities. So if you have two polished metal surfaces moving relative to one another in close proximity, the asperities on the two different surfaces come in contact with one another, and they actually form little welds called micro-welds. And as the parts move relative to one another, the micro-welds are constantly being formed and then fractured and then reformed and then fractured as the two surfaces move with respect to one another. Here's sort of a more schematic diagram of that process, where the asperities contact with one another, form a micro-weld, and then as the relative motion completes, the micro-weld is fractured. And you can see in the right-hand part of this sort of schematic that part of the metal from the lower surface wound up being broken off and torn off by the upper surface. And it's this tearing off of little pieces of metal that is the process that results in wear. So the asperities cause friction, and the fracturing of these micro-welds are the process that causes wear. Friction is the resistance to relative motion. Wear is the loss of material that results from friction. And both are caused by the fracture of these little micro-welds. So that's where lubrication comes in. And the purpose of lubrication is to, I'm not seeing this slide advance, Tim, or, oh, here we go. The purpose of lubrication is to reduce friction wear by preventing or trying to inhibit this process of micro-weld formation and fracturing. And there are several different kinds of lubrication that come into play under various circumstances. Probably the most important in our engines is something called hydrodynamic lubrication, which occurs when a fluid is interposed between the moving parts. It's typically a liquid like oil, although it can be a solid or a gas, but in our engines, it's motor oil is the fluid. And the relative motion of the two surfaces creates a pressure in the fluid, and the pressure is sufficient if the relative motion is fast enough relative to the force that's pressing the two surfaces together. The relative motion creates enough pressure in the lubricant to keep the parts from touching one another. Now, this particular diagram is showing hydrodynamic lubrication with two flat surfaces. So this would be like the lubrication of the piston rings running up and down inside of a cylinder wall. The same kind of hydrodynamic lubrication occurs in bearings, where the motion is between curved surfaces. And that's actually called elasto-hydrodynamic lubrication, but it's the same principle. It's the relative motion of the parts, either the motion of the piston rings moving up and down on the cylinder walls, or the motion of the crankshaft journal turning inside of a main bearing, or the crank pin turning inside of a rod bearing. But it's that relative motion that creates pressure in the lubricant in the lubricant fluid that forces the surfaces apart, so that their asperities don't actually make metal-to-metal contact. And if they don't make contact, then of course none of these micro-welding goes on. So it drastically reduces friction and wear. This is a slightly difficult concept to visualize, this pressure of caused by motion, but the best way to think about it is to think about a water skier who is supported on the surface of a lake because of the motion of the water skier being pulled by the towboat. If the motion slowed down, the pressure that's holding that water skier up would reduce, and eventually the water skier would start sinking. So it's the motion that creates the pressure in the fluid. Another example of this that we're all familiar with is hydroplaning. That if a car is driving on a wet road and it's going fast enough, the pressure of the water interspersed between the road and the tires becomes great enough to actually lift the tires right off the road and eliminate the friction that lets you control the car. So that's the same principle involved in hydrodynamic lubrication. Now, hydrodynamic lubrication works well if the relative speed of the parts is high enough to overcome the load pushing them together. In the same way that, you know, if the speed of the towboat has to be great enough to overcome the weight of the water skier that's trying to sink down to the bottom of the lake. But if the speed is not sufficient relative to the load pressing the surfaces together, then there won't be enough lubricant pressure to keep the parts separated. So if you think, for example, of the piston rings running up and down inside the cylinder walls, in the middle of the piston stroke, the speed of the piston rings moving over the surface of the cylinder walls is quite high, and so there's a lot of pressure built up in the oil film that keeps the rings from touching the cylinder wall. But as the piston gets up to near top dead center, it gradually slows to a stop and then reverses direction and starts going the other way. And as it's slowing and reversing, the speed of the piston rings traveling over the cylinder wall reduces gradually to zero, momentarily to zero. So the pressure that's holding those piston rings off the cylinder walls goes away. And that's one of the reasons why, if you remove a cylinder that's been in service for a while, you'll typically see a pretty well-defined wear step right up at top dead center where the piston rings were reversing direction, because that's where the hydrodynamic lubrication breaks down. So what do we do in circumstances where there's not enough relative motion to keep the loaded parts separated? Well, then we have to rely on a different kind of lubrication that's known as boundary lubrication. Boundary lubrication is lubrication that we depend on where the parts actually are in metal-to-metal contact with one another, because there's not any way to keep them separated. And boundary lubrication relies not on the base oil itself, but on an additive package that's added to the oil. It's actually typically a pretty complicated additive package that is a combination of ingredients that are called anti-wear additives and extreme pressure additives, and they chemically interfere with micro-weld formation as opposed to mechanically interfering with it by keeping the parts separated. Anti-wear and extreme pressure additives both do pretty much the same thing. That is, they chemically interfere with the micro-welding process that causes friction and wear. They're activated in different ways. Anti-wear additives are typically activated by temperature. and extreme pressure additives are activated by pressure. And most engine oils contain a combination of anti-wear and extreme pressure additives that are optimized to provide a boundary lubrication in those areas where hydrodynamic lubrication is not possible. So just as a thought experiment, imagine you rub your two hands together vigorously, and if you do that, you'll feel the friction between them, and you'll actually feel the surfaces of your hands heating up. And believe it or not, what's actually happening is that zillions of little micro-welds are being formed and broken between the palms of your hands. There'll be more friction if you do this right after you wash your hands, because if you haven't washed your hands recently, the skin exudes a little oil film on your palms that will provide some lubrication when you do this. But if you wash your hands and then do it, it'll be even more obvious. Now, if you want to reduce the friction between your two hands as you're rubbing them together, there's a couple of different things you can do. You could coat your palms with Vaseline, for example, and that would drastically reduce the friction when you're rubbing them together by providing hydrodynamic lubrication. Or you could sprinkle talcum powder on your hands, and talcum powder would actually be providing more like boundary lubrication between the two hands rubbing together. Don't take this too literally. This is just kind of a somewhat far-fetched analogy, but it's trying to give you a kind of a mental model to think about these things. So tribologists talk about three different kinds of lubrication: hydrodynamic lubrication, which occurs when you have a relatively low load and relatively high speed that provides enough lubrication pressure in the lubricant to keep the parts separated so they don't touch. Boundary lubrication, where you don't have that pressure and the parts are touching, and you're depending on chemical interactions to inhibit the formation of the micro-welds. And then in the middle, there's what they call mixed lubrication, where there's enough pressure to reduce the contact between the asperities of the opposing parts, but not enough to completely eliminate them. So you're dependent on a mixture of hydrodynamic lubrication and boundary lubrication to minimize friction and wear. So that's about as far as I'm going to go with our little tribology lesson here. Let's talk about the other things that engine oil does. In addition to lubrication, which is what we've just been talking about, we rely on engine oil to clean the engine, to cool it, to seal, to actuate, and protect. And I'll talk about each of those briefly. We already talked about lubrication. Cleaning is a super important function of aircraft engine oil, much more important than in automobile oil. And that's because aircraft engines are literally filthy. They're filthy for a couple reasons. First of all, they're air-cooled engines, so the mechanical tolerances are much, much looser than they are in automobile engines, which are typically water-cooled and held at a much more constant temperature. And because aircraft engines have such sloppy tolerances, plus they have these enormous pistons and cylinders compared to car engines, because they turn so slowly that they have to have very, very large displacements. And so the area of that has to be sealed up by the piston rings is enormous. And an awful lot of combustion byproducts blow past the ring pack in aircraft engines, much more so than in car engines, and get into the oil and contaminate it. So it's very, very important for aircraft engine oil to be able to cope with all of this filth, and to prevent the filth from creating deposits on the inside of the engine, to eliminate sludge. And this problem of filth is vastly magnified by the fact that most of us are still running leaded avgas, 100 low lead typically, in our aircraft engines. And lead is a good octane improver, but it's absolutely disastrous in all other respects. It is a gigantic sludge creator. The lead salts that blow by the ring packs and get into the oil cause all sorts of mischief. And so it's very, very important that our engine oil have the capability to absorb all of this filth that's getting into the bottom end of the engine, and to keep it dispersed so that it doesn't accumulate as sludge, and so that we can drain it out at the next oil change. We'll talk a little bit more about this in a few minutes. But the ability of the oil to keep the engine clean is super, super important in piston aircraft engines, much more so than in automobile engines. Oil in our engines is also a very important coolant. We think of aircraft engines as being air cooled, but if you think about it, there are an awful lot of components that aren't air cooled, and pistons are the most obvious. Pistons are part of the combustion chamber. They run extremely hot. They don't have any cooling fins. They don't have any airflow over them. They're not like cylinder heads or cylinder barrels that we can cool with airflow. The only way pistons get, and they're made of aluminum, which has a really low melting point. So the only way we can keep pistons cool and prevent them from melting is to splash copious quantities of oil onto the bottom of the pistons to carry away the heat. So pistons are not air cooled, they're oil cooled. They're cooled by splash oil. And in fact, as the oil goes through the engine, circulates through the engine, every pass that it takes through the engine, it absorbs enough heat from the pistons and various other hot components that it gains about 40 degrees Fahrenheit on the average in oil temperature as it circulates. And then typically it winds up going through an oil cooler, which dissipates that heat basically it's a radiator that cools the oil back down and dissipates the heat into airflow. And then the oil, having been cooled by the oil cooler, goes and takes another trip through the engine and absorbs lots of heat from pistons and so on. So oil is a very, very important coolant. In a sense, our aircraft engines are partially air cooled, but they're partially liquid cooled, and the liquid that cools them is oil. Oil performs an important function as a sealant in our engines to prevent the leakage of gases and liquids past places that we don't want them to leak. The oil is part of the seal between the piston rings and the cylinder walls. You know, as I mentioned, for most of the stroke, the oil keeps the piston rings physically separated from the cylinder wall in order to reduce friction, and so the oil actually becomes a sealant that is partly responsible for keeping the combustion gases in the combustion chamber. Oil is an important sealant at other kinds of seals, O-rings and gaskets and so on. So it represents an important sealant. in some of our engines, many of our engines, oil is used as a hydraulic fluid to actuate things. If you have a constant speed prop, the propeller pitch is regulated hydraulically using oil pressure. If you have a turbocharged engine with an automatic wastegate, the wastegate is actuated normally through a hydraulic actuator that uses oil pressure to control it. So that's yet another function of engine oil, is as a hydraulic fluid. And finally, but certainly not least importantly, maybe even most importantly, we rely on engine oil to protect our engines, specifically to protect the ferrous metal parts against rusting. And the problem here is that we fly our airplanes a lot less often and a lot less regularly than we drive our cars. At least most of us do. I'm certainly guilty of that, unfortunately. And so the engines sit around a lot, and they have the opportunity to corrode, which is the single biggest enemy of engines reaching TBO. If engines that don't reach TBO typically don't reach TBO not because they wore out. We almost never wear our engines out. It's because they rusted out. And we rely on oil to protect the engine against rust and all kinds of ferrous metal parts, which are vulnerable to rusting, crankshafts, camshafts, lifters, cylinder walls, the gears in the accessory case. All of those are made of steel, or in the case of lifters, chilled cast iron, but all of them are capable of rusting. And the only thing that prevents them from rusting is a protective oil film. And so the integrity of that oil film and the thickness of it and the long lastingness of it and the various corrosion inhibiting additives are all things that are super important in engine oil for piston aircraft engines. And again, the protection function is much more important in aircraft oil than it is in automobile oil, because automobile engines tend to be run, every day or every couple of days. And so the protective oil film is constantly being replenished. Aircraft engines, unfortunately, sometimes sit around for weeks or even months at a time without running, which is really pretty bad for the engine. And we need to choose an oil that has the ability to keep up a protective barrier on the engine to preserve the parts and not let them rust. Talk for a minute about polymers. Polymers are man-made molecules, big giant molecules that are very important then they make up most of our engine oil. Some of the polymers are natural polymers, like mineral oil, things that we drill up out of the ground that came from dead dinosaurs. Others are man-made polymers, the synthetics. The two most common synthetic base oils are called polyalpha olefin, or PAO, and polyalkylene glycol, PAG. And these different polymers that make up the base stock of engine oil have differing shapes. Generally, mineral oil is a much more branchy kind of a molecule. These are kind of highly simplified diagrams just to get the idea across. And synthetic oil tends to be a lot smoother and less branchy. Now, the advantage of synthetic oil, of having this nice smooth molecule that doesn't have a lot of side branches, first of all, synthetic oil is slipperier. It has greater lubricity, I guess is the correct term. Also, it's longer lasting. Mineral oil gradually degrades the longer it remains in service, because as the mineral oil it sits between a pair of moving surfaces, the little side branches on the polymers tend to shear off, which is a phenomenon called polymer shearing, and that causes the viscosity oil of the mineral oil to decrease over time, whereas synthetic oil tends to hold its viscosity constant over a much longer period of time. And that's why synthetic oil, because it's less branchy and doesn't suffer from this polymer shearing as much and retains its viscosity better, it can go a lot longer between oil changes in automotive applications. But that's not so much true in aviation applications. And the reason is that when we change the oil in an airplane engine, we're typically not changing it because the oil has gotten old and is broken down. We're changing it because it's full of filth that we want to get out of the engine. And the oil only has a capacity of holding so much filth before it starts settling out and creating sludge. So our oil change intervals in aircraft are really more filth driven than they are driven by the breakdown of the oil itself. And mineral oils' branchy molecules, although they're not as slippery, they do a much better job of holding particulate contaminants in suspension so that they can be drained out at the next oil change. And this was highlighted back in the 90s when Mobil had introduced an aviation version of its Mobil AV1, Mobil 1 synthetic oil, which was very successful, all synthetic automotive oil. But Mobil introduced an aviation version of that called Mobil AV1, became very popular for a while. And then all of a sudden, people started realizing that it was realizing that it was wrecking engines. And it was wrecking engines because the engines were getting loaded up with lead sludge. And it turned out that this all synthetic oil, which was, I think it was polyalpha olefin based synthetic oil, it simply couldn't deal with the lead blow-by in piston aircraft engines. And so these engines would get contaminated with lead sludge. And ultimately, Mobil pulled AV1 off the market in a hail of class action lawsuits from owners whose engines had been ruined by it. And so since that happened, there have been no all synthetic aircraft engine oils on the market. There are some semi-synthetics on the market, notably Aeroshell 15W50, which is 50% synthetic and 50% dead dinosaurs. But this just went to illustrate the fact that synthetic oil, although it has a lot of advantages, has one gigantic disadvantage in terms of piston aircraft oil, and that is it simply doesn't deal with filth very well. Even with a semi-synthetic like Aeroshell 15W50, which is only half synthetic, we've seen a lot of very serious lead sludge problems, causing premature removal of cylinders, premature escalation of oil consumption, and so on, in engines that have large displacements and small oil sumps. And the place we've seen this the most, mostly because we manage a lot of these airplanes, is in the Cirrus SR-22s. Cirrus SR-22 is powered by a Continental IO550N engine, which has a very big displacement, 550 cubic inches, and a very small oil sump. It only has an 8-quart capacity, and most owners run it at about 6 quarts, because if you run it at 8 quarts, it kicks the first 2 quarts out the breather pretty quickly. So you're asking a small quantity of oil, 6 quarts of oil, to absorb the filth from a very, very large displacement engine, a 550 cube engine. And if the oil you're using is a semi-synthetic, where half of the oil can't hold lead sludge in suspension because it's synthetic, you're basically asking 3 quarts of oil effectively to hang on to all of this lead sludge, and it just can't do it. So I'm not a big fan of using synthetic oil in piston aircraft engines, as long as those engines are being operated on unleaded avgas. Now, some of you are running unleaded MoGas, and synthetic oil is great for that. The Rotax 900 series is sort of optimized for unleaded MoGas, and most people who run Rotax engines and run it on MoGas use all synthetic oil. And I think once we are able to get rid of leaded avgas and start using all unleaded avgas, then I think we're probably going to all go back to all synthetic oil, because it has so many advantages, but its huge disadvantages. It just can't deal with filth, particularly filth from leaded fuel. And so, as long as we're running unleaded fuel, it's a good idea to steer clear of the synthetic oil, I think. Talk a little bit about monograde versus multigrade oil. To make a multigrade oil, like Aeroshell 15W50 or Phillips 20W50, you start with a thin monograde oil, and then you add an artificial thickening agent. This is another man-made polymer called a viscosity index improver, or VI improver. And the VI improver is a very interesting polymer. It's a polymer that rolls up in a tight little ball, but as it warms up, the ball kind of unfolds. And the result is that this VI improver, this man-made molecule that rolls up in a ball, has the unusual property that its viscosity increases. It gets thicker and more viscous when it's heated, which is exactly the opposite of what mineral oil does. The oil gets thinner as it's heated. VI improvers get thicker as it's heated, as they're heated. So by mixing VI improver into mineral oil, you can get pretty much whatever viscosity index curve you want. In other words, how the oil's viscosity varies with temperature. You can control it to do pretty much whatever you want by having the right balance of oil and VI improver. Now, you don't want to put too much VI improver in the oil, because VI improver isn't a very good lubricant. So we want the oil to be mostly oil, but and typically in multigrade oils, about 10% of the oil is VI improver. And but at any rate, that's how multigrade oil works. It's a thin oil to which this VI improver molecule is very unusual molecule. It balls up when it's cold and sort of unrolls when it warms up. Is added to create the appropriate viscosity index curve that is desired. So a multigrade oil rated as 20W50, like the Phillips XC product, is basically an SAE 20 oil, to which about 10% of VI improvers are added to obtain a viscosity of SAE 50 oil at 100 degrees Celsius boiling point of water while maintaining SAE 20 at freezing, 0 degrees Celsius. And that's what the 20W50 rating means. It means that the oil measures SAE 20 at freezing and SAE 50 at boiling, and that's how these ratings work. And this is accomplished by taking the oil, thin oil like SAE 20 or 15 or something, and then adding enough VI improver to thicken it up to the degree that's desired at operating temperature. So at full operating temperature and operating temperature of oil, we optimally look for oil temperature on the gauge is about 180 to 200 Fahrenheit is just about perfect. And by the way, that temperature that's on the gauge is the temperature of the oil at the coolest part of the cycle. So at the hottest part of the cycle, it's about 40 degrees higher than that. So if you see 200 on the gauge, it means that the oil temperature varies from about 200 as it passes the probe up to about 240 when it at its hottest point, right before it enters the oil cooler. But at operating temperature in the 200-ish area, boiling point of water-ish area, Aeroshell W100 and Phillips 20W50 have the same viscosity. They're both SAE 50 oil, but at freezing, there's a huge difference in porability. The 20W50 oil pours like tomato juice, and the monograde oil, 100 grade oil, SAE 50 oil, pours like ketchup. But they have pretty much the same viscosity up at operating temperature. Now let's talk a little bit about additives. Oil additives are absolutely vital for both lubrication and longevity of the engine. And without them, the oil would become contaminated, it would break down, it would leak out, and it would not properly protect the engine parts against rust. Typical aircraft oil is something like this. It's 3/4 or so base oil and 1/4 a combination of various additives, VI improvers if it's a multi-grade oil, and a cocktail of anti-wear, anti-corrosion, and other kinds of additives that we'll briefly touch on here. We've already talked about VI improvers. Those are those magic little balled up polymers that modify the viscosity of the base oil to create a multi-grade oil. And we've talked about anti-wear and extreme pressure additives that chemically react with metal surfaces to inhibit micro-weld formation chemically in the boundary layer regime, where we don't have enough lubricant pressure to keep the parts separated. And again, anti-wear and extreme pressure additives pretty much do the same thing, but they're activated a little differently. Anti-wear additives are typically temperature activated. Extreme pressure additives are pressure activated. So that, for example, what we depend on to prevent cam and lifter wear is primarily extreme pressure additives, because those parts run pretty cool, but they're under extremely high pressure at the contact points. And so we rely on an extreme pressure additive such as triphenyl phosphate is the stuff that's in that Lycoming LW16702 snake oil additive. It's an extreme pressure additive that's used to help increase boundary lubrication at the cam and lifter interface. Or friction modifiers that improve oil lubricity by making the oil more slippery. There are anti-foaming agents that modify the surface tension of the oil so that it doesn't create a lot of bubbles. It allows the bubbles to burst and minimizes foaming. Corrosion inhibitors, super important additives that help reduce the rusting of steel engine parts by forming a chemical barrier. They're polar chemicals that form a barrier on the metal to protect them from moisture when the engine is inactive. Tackiness agents that increase the oil's adhesive property to keep the film stuck to the parts and protect them better. We have acid neutralizers. There's a lot of water created when an aircraft engine runs because the combustion of hydrocarbons creates the two chemicals that come out of the production of hydrocarbons primarily are carbon dioxide and water. And most of that water goes out the exhaust pipe in the form of steam, but some of it blows by the rings and gets into the bottom end of the engine and builds up in the oil. And you can tell that when you come in from a flight, you pull the dipstick out. Typically the oil cap is covered with moisture and stuff, and that's moisture that was generated by the process of combustion and got into the bottom end of the engine because it blew past the rings. That water combines with sulfur and other things to create sulfuric acid and some hydrochloric acid and some carbolic acid, and so the oil has to have acid neutralizers that will neutralize the acid and protect them from buildup. And of course, those acid neutralizers are consumed in the process of neutralizing acid. And so the oil only has a capacity to neutralize a certain amount of acid, which is another reason that we want to drain it pretty regularly in order to put fresh oil in and put a brand new additive package back into the engine. There are oxidation inhibitors that prevent the oil from premature aging at high temperatures. And there are detergents and dispersants which help keep engines clean and free of deposits by holding combustion contaminants in suspension and preventing them from forming sludge and varnish deposits. Now, the difference between detergent and a dispersant is basically that a detergent dissolves and cleans the sludge off once it's formed. And a dispersant holds the particulate matter in suspension and prevents it from precipitating out as sludge. Detergents are typically metallic-based chemicals, typically have zinc in them. They're often found in automotive oils, although there's sort of a trend towards non-detergent automotive oils. But detergents, because they're metallic, can create ash that can cause pre-ignition in aircraft engines. And so we don't use detergents in aircraft engine oil anymore. We still use them sometimes in motor oil for cars, but we don't use them in aircraft engine oils. We use dispersants instead, which is why piston aircraft oils are called ashless dispersant oil or AD oil. And the dispersant is basically a polar chemical with a head that's attracted to contaminants and a tail that is soluble in oil, and they form a little capsule around the particulate matter and keep it suspended and prevent it from forming sludge until we can drain it out at the next oil change. So, bottom line, what oil do I recommend? Look, all of the piston aircraft engine oils on the market today are excellent oils, and there's a pretty wide range of oils available. They all do a good job if you change the oil and filter regularly, and I recommend at least every 50 hours or 4 calendar months, whichever comes first. If you fly a lot, it'll be every 50 hours. If you don't fly as much, it'll be 4 calendar months. But we want to get the filth out of the engine, so we want to drain the oil regularly. Our oil change intervals for aircraft engines, or again, they're not driven so much by oil breakdown. They're driven by filth, and how much filth the oil can hold in suspension. We really want to get rid of it. Also, how much acid it can neutralize, stuff like that. And also trying to keep your oil temperatures in the sweet spot, which is in the 180 to 200 degree range, as indicated on the gauge. If the oil temperature is much higher than that, say higher than 210, for a prolonged period of time, the oil will tend to oxidize and break down. If the oil temperature is much lower than that, say below 170 degrees for long periods of time, then the moisture will tend not to be boiled off and expelled from the engine through the breather, and you'll tend to get a moisture buildup and an increased possibility of corrosion. So that's why this is kind of the sweet spot. At higher altitudes, if you're flying up in the teens or the flight levels, we can allow oil temperature to get lower than that, because the boiling point of water is a lot lower than that up at high altitudes. Personally, I prefer to use monograde oil if you don't have a need for multigrade. The thing to remember is that multigrade oil is not 100% lubricant. It's got these VI improvers in it, which help modulate the viscosity, but don't do any lubrication. And so if you operate in a temperate climate like I do, I'm based in California, I would be inclined to use a monograde oil. In fact, I do use a monograde oil in my airplane. If you operate in an area of where it gets real cold, then the multigrade oil is pretty much a necessity. As I mentioned, I don't like synthetic or semi-synthetic oils for engines that run on leaded avgas. There aren't any more synthetic oils available right now for aircraft engines, unless you're running a Rotax or something. But 15W50 Aeroshell is one of the most popular oils, and it's semi-synthetic. And if you're running leaded avgas, particularly if you're running a large displacement engine with a not so large oil sump, I would steer clear of the semi-synthetic. Again, once we get to the point where we're running unleaded fuel, then synthetics will be the oil of choice. But as long as we're running unleaded avgas, I think it's a good idea to stay away from synthetics. And so for my clients that need to run multigrade oil, I normally steer them towards the Phillips product because it's 100% dead dinosaurs, no synthetics. And finally, I've become a big fan of an oil additive called ASL CamGuard because it has outstanding anti-rust properties. It's the best thing I know of to prevent rusting of a engine that it's used irregularly, like a lot of our owner-flown airplanes are, and certainly mine is. It also has a very good anti-wear package in it, and so I've been using CamGuard, Aeroshell W100 monograde plus CamGuard in my Cessna 310 for decades, and I've gotten phenomenal longevity out of my engines doing that. And they, my engines are not really the poster child for lasting long, because I fly irregularly, and my airplane is based pretty close to the coast, and which is a high corrosion environment. And yet, with this combination, I've done extraordinarily well. So key takeaway from all of this in selecting your oil and additives for your engine, I think more than lubrication, probably the two most important considerations are picking an oil that will do a good job of inhibiting corrosion, And I like a nice gooey, thick single weight oil with something like CamGuard added to it, and dealing with filth. And for that, I like using dead dinosaurs, not synthetics, and draining it on a very regular and fairly frequent basis. Once we start running on unleaded avgas, we'll have a lot less filth, and we'll be able to change our equation a little bit. That was pretty long, Tim, but that's all I have. So I guess we probably got a half an hour for some Q&A.
Fantastic. That was just great. A lot of questions coming in here. Let's talk first about a couple of people are kind of wondering Bradley's question here. If you live in a cold climate, you know, during the winter, hot in the summer, so you got variable climate, hot summers, cold winters, do you recommend switching oil weights based on the season?
You know, I personally think that would be optimal. To run on a thick single weight oil during the hot season and run on a multi-grade oil during the cold season. It's not absolutely essential, and we've had pretty good luck with aircraft up in the North Country running Phillips XC with CamGuard. The summertime is when we're most concerned about corrosion, because there's a lot more moisture in the air and so on. And the day-night temperature cycle that drives the condensation cycle in engines is much more pronounced during the summertime. That's when we're really worried about corrosion. Less so in the winter. In the winter, we want to just make sure that, you know, we get oil pressure coming up during cold starts and so on. So, you know, I think that the absolute optimum for somebody that lives in a climate like that would be single weight oil in the summer and multi-grade oil in the winter with a good additive package in both. But we've had pretty good luck just running the Phillips 20W50 all year round.
And Ralph's kind of wondering, if you preheat your engine during the winter when it's cold out, is there any good reason why you would switch and not just continue using W100?
No, other than the fact that if you use your airplane for travel, then you sometimes will wind up overnighting someplace away from home where you don't have the opportunity to preheat. But if you can consistently preheat, then yeah, there's no reason to not just run monograde oil all the time.
Preston's wondering, at the air show, I got a nice case rate and bought 2 cases of oil. Does oil have a shelf life?
There actually is a published shelf life. I forget what it is. It's a number of years. I've never run into an issue of oil actually going bad. I think it's probably its effective shelf life is, I would guess it would probably be fine for 10 years or so. We never seem to run into a problem of old oil causing problems.
Mylan is wondering, is there any benefit in using 1 quart of a synthetic blend with 6 quarts of a monograde oil?
I can't think of any. No, I don't think so. I really don't think so. Like I said, once we're able to run our engines on unleaded fuel, and some of you are running on unleaded fuel. I mean, some of you are lucky enough to be able to run on unleaded mogas, which has the advantage both of being cheaper and also being a whole lot cleaner. And if you're running unleaded fuel, then I would recommend running an all synthetic oil. But if you're running avgas, then I would recommend running an oil that is basically mineral oil, uses a mineral oil base because that holds the lead salts in suspension a lot better. And you know, as I mentioned, the lubrication demands of our engines are typically very, very modest, and so the focus should really be on keeping the engine clean. Pretty much any oil is going to provide adequate lubrication, but we really need to keep the engines clean, and we really need to protect them from rusting. Those are the two big priorities, I think, in thinking about what oils to use.
Craig is wondering, why does oil consumption go up on long cross countries and as the oil nears change time?
Well, I'm not aware that it goes up on long cross countries. That may have something to do with how you're measuring it. Um, if you're measuring oil consumption by looking at the dipstick, um, the only accurate way to do that is to check the dipstick when the engine is ice cold, because after you come in from a flight, there's a lot of oil adhered to various parts and stuff that takes literally hours to drain back into the crankcase and show up on the dipstick. There is a good reason that oil consumption gradually goes up as the oil gets more time on it, and that is, we actually talked about it, is this effective polymer shearing, which causes the oil's viscosity to gradually degrade the longer it's kept in service. This is really a problem primarily with mineral-based oils, not with synthetic oils. But since there are no all synthetic aircraft oils, we're all using mineral oil to some degree or other, and the viscosity will gradually get less due to polymer shearing as the oil remains in service over time, and that's another reason why we want to change it fairly regularly.
Steve says, my oil turns black after a short period of time, usually 5 to 10 hours. Should I change the oil more frequently?
Well, you should, but also you should, if your oil turns black that quickly, it means that you have excessive blow-by, and you probably want to try to figure out where that's coming from. And the best way to do that is to bore scope the cylinders and take a look at the condition of the cylinder barrels. But that's a tip off of excessive blow-by past the rings is the fact that the engine oil turns dark very quickly, and it may just be one cylinder that's the culprit, that's blowing by a lot of crud. So I would take out the top spark plugs and stick a bore scope in the hole and look around and see what you can see.
David's wondering, how important is making sure the oil is hot when you're draining it for an oil change?
Well, it's a good idea because you'd like to get as much of the dirty oil out of the engine as you can, and the cooler it is, the thicker it is, less likely you're going to get it all out. Of course, you never get it all out. There's always oil trapped in propeller hubs and oil coolers and things that don't drain out. But you'd like to try to get as much of the oil out as you can when you change the oil. It's more important to do that if you're running a monograde oil like I do, because it gets so thick when it cools down. It's a little less important if you're running multigrade oil, which stays pretty pourable even at room temperature.
Grover's just wondering, what type of oil is recommended for breaking in a new engine?
Well, I could say come back in January for Builders Week, because I'm going to be doing a webinar on break-in. Actually, there is a webinar that I did on break-in a while back that's on the library. But basically, the traditional oil that's used for engine break-in is what they call straight mineral oil, which has no ashless dispersants and minimum of additives. I think that's more tradition than anything else. I've never seen any indication that that an ashless dispersant, simple ashless dispersant oil like Aeroshell W100 isn't just as good for engine break-in. The two things you want to avoid when you're breaking in the engine, because if you think about it, what are we trying to do when we break in the engine? We're actually trying to get metal to metal contact between the piston rings and the cylinder walls, because we're trying to smooth off those sharp peaks of the asperities a little bit. That's what break-in is all about. And so we have the opposite objective during break-in as we have during normal operation, which is we're actually trying to get some metal to metal contact. So that's why, first of all, it's really important to run the engine very, very hard during the first couple of hours to create as much load pressure between the rings and the cylinder walls as possible. But we also want to avoid using oil. First of all, we want to avoid any synthetics because the synthetic has a stronger film strength than mineral oil, and it's harder to break through that film and get the metal to metal contact we're looking for. And the second thing we want to avoid are friction modifiers, anti-wear, anti-scuff, extreme pressure additives. So you wouldn't want to put cam guard in there. You wouldn't want to put Lycoming LW16702. You'd rather avoid oils like Aeroshell W100 Plus or Aeroshell 15W50 that have a lot of anti-wear, anti-scuff additives that are pre-blended in. You like to use a pretty simple oil. So either a straight mineral oil or a simple ashless dispersant oil with minimum additive package works really well for break-in. Phillips actually makes an oil that's called Type M, which is a multi-grade oil with a minimal additive package that's specifically designed for break-in. I've had pretty good luck using Aeroshell W100. A lot of people use Aeroshell 100 without the W, which is a straight mineral oil. It doesn't have ashless dispersants. If you use straight mineral oil, my only caution is don't leave it in there very long. Drain it out because it doesn't have the dispersants required to keep the engine clean. So the longer you run it, the dirtier the engine's going to be inside. So get rid of it after no more than 10 hours, preferably less.
Many people are kind of asking about the difference between W100 and the W100 Plus. And is there any advantage in using the Plus versus the straight 100 and cam guard, for example?
Yeah, well, W100 Plus it's actually an oil that years ago John Frank and I nagged Shell into coming out with. Their product support guy was a guy named Ben Visser, who's long since retired, and we talked to Ben and said, you know, Ben, we'd really like to be able to use the additive package that's in Aeroshell 15W50, but we don't like the synthetic and we don't want the multi-grade. Couldn't you take that same additive package and stick it into W100? And ultimately Shell did that. And it came out with this oil called W100 Plus. So W100 Plus is basically W100 with some additional anti-wear agents and some additional corrosion inhibitors. And it's not bad stuff. I personally think that adding cam guard to W100 is a better solution than W100 Plus because I like the cam guard additive package a little bit better. But if you're not in an area of extreme corrosion risk, W100 Plus is a good oil. And again, it's basically W100 with an enhanced additive package that has some additional anti-wear stuff in it and some additional anti-corrosion additives in it.
Several people are wondering about oil analysis. Do you recommend it? William wonders, should it be done at every oil change?
I do recommend oil analysis, and I do recommend doing it at every oil change. It's pretty inexpensive. It's important to understand what oil analysis is good for and what it's not good for. Oil analysis detects microscopic wear metals and other contaminants in the oil that you drain out of the engine. And so it's very good at seeing very slow wear events. For example, accelerated wear of an exhaust valve stem against an exhaust valve guide. Those are two very, very hard surfaces, and they wear very slowly, and they throw off little microscopic pieces of metal. And the metal that they throw off is pretty easy to identify in oil analysis because the guide is a very high temperature alloy that has a lot of nickel in it. So if you see elevated nickel in your oil analysis, assuming that you're not running nickel plated cylinders, you can be pretty sure it's coming from the exhaust valve guides, and it'll detect it very, very early. Another thing oil analysis is really good for is detecting dirt getting into the engine, which can cause things to wear quite rapidly. And dirt shows up in oil analysis as elevated silicon. And if we see elevated silicon in oil analysis, we start looking for leaks in the induction system, something like a carburetor heat door or alternate air door that's not sealing, or maybe an induction air filter, or maybe something chafed into one of the induction tubes. So oil analysis is really good for stuff like that. What oil analysis is not good for is detecting rapid wear events, things like cams and lifters coming apart, because those things happen quite rapidly and they throw off quite relatively large pieces of metal. And the metal that's thrown off from cam and lifter wear is almost all caught by the oil filter. And so it won't wind up in the sample jar, and you won't see it in oil analysis. You'll see it in oil filter inspection, especially if you inspect it with magnifying glass, but you typically won't see it in oil analysis because the wear metal that comes from those events is too large to wind up getting into the oil analysis sample without being filtered out by the filter. So as long as you understand what it's good for, I do recommend it. I do it on my own airplane. And I'm also very careful about inspecting the oil filter. And as if you do both of those, then you can be pretty sure that regardless of whether it's a fast or a slow wear event, whether it's throwing off larger pieces of metal or microscopic pieces of metal, you'll be aware of it. So it's not a replacement for oil filter inspection by any means. It's a supplement to it, but I think it's a worthwhile thing to do.
Thomas is wondering, what are the most common causes of high oil consumption?
Well, by far the most common is high blow-by caused by something that's causing the rings not to seal well against the cylinder walls. So you wind up getting excessive pressure in the crankcase when the engine is running because the rings aren't sealing the combustion pressure well enough. That high crankcase pressure, when the engine is running, the crankcase is full of oil mist that's being thrown in every direction by the spinning crankshaft. And so if you have high crankcase pressure, you're going to get quite a breeze going out the engine breather, and that breeze is going to be carrying this oil mist with it. When people have high oil consumption, and again, I think I've done a webinar on this subject, there's sort of some basic things you look for, because the oil has to be going somewhere, and the question is, where's it going? And one place it can be going is out the engine breather. That's the most common thing. That's what I just described, where you have high blow-by, high crankcase pressure as a result of the high blow-by, a lot of airflow out the breather that's carrying a lot of oil mist out. And it reveals itself typically by a lot of oil on the belly of the aircraft that emanating from right behind where the breather tube um, exits the cowling. A second cause of oil consumption is oil that's actually consumed in combustion. That can be caused by things like a bad oil seal or a worn intake valve guide or valve stem that's letting oil get sucked into the cylinder and consumed in combustion and thrown out the exhaust pipe. And if that's the case, then you won't see a lot of oil on the belly. What you'll see is like a black oily deposit on the inside of the exhaust pipe, as opposed to the nice dry kind of brownish powdery thing that you normally would see on the inside of the exhaust pipe. The third and probably the least common reason for high oil consumption is that there's an oil leak someplace. But that's usually pretty obvious, because a little oil leaking out of the engine makes just a gigantic mess under the cowling. And so if you had an exhaust or a oil leak, you would definitely know it at the next oil change. And that's probably the least common reason for oil consumption. But basically, when you're dealing with high oil consumption, the first step is to say, hey, which of those three places is the oil going? Is there oil on the belly? Is there an oily deposit inside the exhaust pipe? Or is there an oily mess inside the cowling? It's got to be one of those three things, because the oil has to be going somewhere.
Many people have asked this question. Now I'll use Mark's. What is the proper proportion of cam guard to engine oil?
The normal concentration is 5%, which means 1 pint of cam guard treats 10 quarts of engine oil. It's not highly critical. It doesn't hurt to use a little extra. So, you know, if you only have an 8-quart sump, it's still okay to dump a pint of cam guard in there. You don't have to get OCD about it. In fact, Ed Collin, who is the lubrication chemist who developed cam guard, used to run the Exxon engine lab for many years. He actually recommends using a 10% mixture of cam guard and oil if you are trying to pickle the engine. If the engine's going to be inactive for a period of months, and you want to pickle it against rust. So anything up to 10% is acceptable, but 5% is the normal concentration of cam guard.
And Ray is just wondering, is it okay to mix oil brands? Is it okay to mix oil viscosities?
Absolutely yes and yes. All oils that are currently on the market are compatible with one another. They all meet the same mil spec. Continental came out with this weird service bulletin some months ago that was trying to discourage people from changing oil brands. And I have absolutely no idea why they did that, because there's absolutely no science behind that. It had to be some sort of warranty thing or something. With maybe the lawyers made them do it. I don't know what it was, but no, there's no problem changing oil types, oil brands. The only thing is that you know, if you start mixing oils and you're doing oil analysis, you may get some slightly weird results, because, you know, for example, W100 plus has a lot of phosphorus in it, and W100 doesn't have any phosphorus in it. And so usually when I look at an oil analysis report, I can tell what brand of oil the guy's using. But if you're doing a mixture, it gets a little confusing. But other than that, no, there's no real problem at all mixing different brands of oil. And I've certainly, you know, thrown a quart of 20W50 into my sump that's full of W100 just because I happen to have it and needed a quart of makeup oil. It doesn't hurt anything.
William is wondering if the plane isn't flown frequently, like in the winter, is it a good idea to run the engine for a short time, 15 minutes maybe each week, to circulate the oil to all surfaces?
It's actually a double-edged sword. I don't recommend it, and the reason is, you know, the plus of doing it is that you reestablish the oil film, and the minus of doing it is you generate a big slug of water. And because the oil never gets up to full operating temperature, um, the water never gets purged. So if you do it repeatedly, you're going to build up a gigantic quantity of moisture in the oil. So if you want to run the engine, um, then run it long enough and hard enough, at least to get the oil temperature up to full operating temperature for several minutes, which will allow the moisture to boil off and be ejected out the engine breather. But doing a short run where the oil temperature doesn't get up to 180 or so, it's a real mixed blessing, and I don't recommend it.
Stephen is wondering, with clean oil being paramount, are you a strong proponent of oil filter adapters on engines that normally have a standard screen?
Oh, without question. Any engine that still has a suction, a pressure screen, it's a really good idea to retrofit it with a full flow oil filter, and it's a really good idea for two reasons. First of all, it does a much better job of filtration, but probably even more than that, it does a much better job of being able to detect any metal that the engine is making, because it's much easier to detect metal inspecting the fan fold filter media of a full flow oil filter than to try to see metal on a conventional pressure screen. So there are two really good reasons for doing it, and the kind of the clincher is that adding a full flow oil filter will double your oil change interval, and so it pays for itself very quickly. So it's just a really good idea, and I would recommend it to anybody who's operating an engine that doesn't have a full flow filter to add one. There are a variety of adapters available, some that mount right on the engine, and some that mount remotely on the firewall with some hoses that lead there. And which one is best kind of depends on your your engine installation and where you have room to put it. But it's definitely worthwhile.
Well, Mike, fantastic presentation. Many comments thanking you for it. It looks like we probably had about 1,300 people at least logged in at the high there. So great webinar. Thank you. Please share your closing thoughts with everybody. And everybody had great series of questions.
That sets a record, right?
It is, I think, yes.
Oh, that is so cool. Well,
By far.
thank you everybody for coming. Well, I'll make this quick. I've still got 4 books available on Amazon. If you don't have any of them, you're invited to get your hands on them. They're available both in paperback and in Kindle versions that you can play back on whatever device you like. And if you do have read the book, I would really appreciate it if you'd go and post a review on Amazon. I am working on turning these 4 books into audiobooks, and I'm almost done with Manifesto. I'll be releasing that on Audible by the end of the year. And if you'd like to support my work on that and these webinars and all the other outreach stuff that I do, you can support me by going to my Patreon page at patreon.com/ Savvy Aviator. And finally, the next 3 webinars, first Wednesday of the month, except for, I guess, January. We decided it's going to be the second Wednesday of January, because, is that right? I'm trying to
Well,
remember.
you caught me off guard here.
I
I'm not sure.
don't remember whether we had to make an adjustment for New Year's or how that worked. No, maybe no, I guess it maybe is the first Wednesday. Any rate, these are the next 3 webinars. December webinar entitled "Good Eyes, Great Catch" talks about the importance of picking an experienced mechanic with an experienced set of eyes to try to run down difficult problems that are elude less experienced mechanics. In January, the webinar is called "It's Baffling," and it's all about engine baffles and engine cooling problems and so on. And finally, in February, webinar called "How Mags Work" that will be talking about magnetos. I think that's going to be the first of a 2-parter. We'll do in February how mags work, and I think in March we'll do how mags fail, talk about the various failure modes of magnetos and what we can do to prevent mag failure and how to react to mag failure when it happens in flight.
That'll be a good one. Yeah, that'll be really good. Hey, January 6th is the first Wednesday. However, the year is 2021. You're going to be doing
oh,
that.
gee. Uh-oh. Yeah, how right you are. Okay.
You put 2020 up there just to see if we'd catch it.
Okay. You want to hang around? I'll fix the slide, but
No,
okay.
that's fine. I think we all got the message.
Am I allowed to do something like, oh, I thought maybe I could.
Oh, now you're getting technical on us.
I didn't mean to do that. I meant to do.
You're going to change it?
I meant to do this or something.
Oh man, I love it. Using the drawing tools.
I don't know. At any rate. Any rate, I think I've overstayed my welcome, but thank you everybody for coming and setting an all-time attendance record, and look forward to seeing you guys next month.
Thank you so much, Mike. Wonderful presentation. Thank you so much. Everybody who joined us tonight, thank you so much for logging in. Have a wonderful evening. Hope you can join us next week.
Night, everybody.